You are tuned to Iri-e-learning, and I am your host, Teacher. In this acids, bases, and salts lesson, we will examine strength versus concentration for acids and bases. Check the description box for links to all the videos related to this unit. By the end of this lesson, we should be able to explain the terms strength and concentration of acids and alkalis, relate the strength of acids and bases or alkalis to pH values, differentiate between the strength and concentration of acids or alkalis. The first learning objective of this lesson is to explain the terms strength and concentration as it relates to acids and alkalis. So we will start by explaining the term strength of acids and alkalis. The strength of a solution, whether it's an acid or an alkali, depends on how much the solute molecules dissociate into ions. And by dissociate, we mean the molecules separate into the respective cations and anions. The strength of a solution is characterized or described using two terms. First, strong, and this means that the solute molecules of the acid or the alkali ionizes or dissociates completely. And the second term is weak, and this is when the solute molecules of the acid or the alkali partially ionizes. Direct your attention to the animation on the left of the screen while the explanation is given for a strong acid or alkali. Now, an acid or an alkali solution is described as strong when all the solute molecules, meaning the molecules of the acid or the alkali, which is represented as AB in our animation, is separated or dissociated into the ions. And this is called complete dissociation. So now what we have are cations which are positive and anions which are negative within the solution of the strong acid or alkali. So you won't find any solute molecules as before, which we represented as AB. Once again, look at the animation while the explanation is given for a weak acid or alkali. Now, the solute molecules of weak acids or alkalis will only partially ionize or dissociate in solution. Therefore, within a solution of a weak acid or alkali, there will be a mixture of the solute molecules represented as AB and a few cations, the positive ions, and anions, which are the negative ions in the solution. We will now take a specific glance at the strength of acids. Recall that the strength of an acid is described as strong or weak. All the solute molecules of a strong acid, represented by HX in the animation to the right of the screen, will ionize or dissociate completely in solution, releasing all their hydrogen ions and associated anions. Therefore, strong acids release or contain their maximum number of hydrogen ions in solution. Examples of strong acids include hydrochloric acid HCl, sulfuric acid H2SO4, and nitric acid HNO3. Now we'll take a look at the ionization of a strong acid such as hydrochloric acid HCl. Each molecule of hydrochloric acid within solution will ionize and separate to give one hydrogen ion and one chloride ion. Therefore, the ionization of a hydrochloric acid molecule is represented by the ionic equation HCl dissociating into one hydrogen ion and one chloride ion, all in aqueous solution. Hence the state symbol AQ, just simply mean they're dissolved in water. So when the HCl dissolves in water, it releases the hydrogen ions and the respective chloride ions. As a result, a solution of hydrochloric acid will always and only contain hydrogen ions and chloride ions. There are no HCl molecules present. Next, we will look at the ionization of sulfuric acid, chemical formula H2SO4. And of course, sulfuric acid is an example of a strong acid. A molecule of sulfuric acid contains a sulfate radical to which two hydrogen atoms are bonded. Therefore, a molecule of sulfuric acid will dissociate into two hydrogen ions and a sulfate ion, SO4 2-. As a result, the ionization of sulfuric acid is represented by the ionic equation H2SO4 aqueous dissociating into two hydrogen ions and a sulfate ion, and they're all dissolved in water, hence aqueous. Consequently, a solution of sulfuric acid only contains hydrogen ions and sulfate ions dissolved in water. There are no sulfuric acid H2SO4 molecules present because all have dissociated dissociated into hydrogen ions and sulfate ions. Now we'll examine the ionization of the strong acid, nitric acid HNO3. The molecule of nitric acid will dissociate to give a hydrogen ion and a nitrate ion, NO3 minus, and of course the hydrogen ion is H plus. Therefore, we represent the ionic equation for this dissociation as HNO3 aqueous dissociating into one hydrogen ion and one nitrate ion. And since nitric acid or nitric acid is a strong acid, its solution will only contain hydrogen ions and nitrate ions dissolved in water. There will be no HNO3 molecules present because all these molecules have dissociated into their respective ions of hydrogen ion H plus and NO3 minus the nitrate ion. We just looked at strong acids. Now we will examine weak acids. When weak acids dissolve in water, some unique things happen. 1. Weak acids partially ionize when in aqueous solution, that is, only a few acid molecules dissociate into ions at any given time. Secondly, some of the dissociated ions will rejoin to reform acid molecules. And thirdly, the process or change keeps going forward and backwards and is called a reversible reaction. The reversible reaction is depicted by the two-way half arrows that we see right here, and the half arrowheads indicate the direction in which the reaction goes at any given time. So this is our forward reaction and our backward reaction half arrowheads. So in a solution of a weak acid, there will always be weak acid molecules mixed with ions, such as the hydrogen ion and the respective anion. Examples of weak acids include the following organic acids: methanoic acid, HCOOH, which is naturally occurring in the sting or venom of ants and bees; ethanoic acid, CH3COOH, which is found in vinegar; and lactic acid, CH3CH2OCOOH, which is found in sour milk and overextended muscles after exercise or other strenuous physical activity. It usually causes sore muscles. It is important to highlight that although organic acids have many hydrogen atoms in their formula, only the hydrogen at the end of the COOH group is acidic or replaceable. The COOH group is called the carboxyl group. And we'll learn a little more about organic acids when we get to organic chemistry. We will now look at the principle of ionization in a weak acid using ethanoic acid as an example. The chemical formula of ethanoic acid is CH3COOH. Recall that only a few ethanoic acid molecules, as it's a weak acid, will dissociate into ions, but those that dissociate will release one hydrogen ion and the ethanoate ion. So in the forward reaction, we spoke about the half arrow representing the direction in which the reaction is going. So for the forward reaction, we will have CH3COOH molecules dissociating into the ethanoate molecule, and the hydrogen ion is released from the end of the COOH group, the carboxyl group. Also recall that some dissociated ions will recombine to reform the acid molecules in the reverse reaction, hence the use of the reversible arrows. We write the ionic equation as CH3COOH in a reversible process, releasing the ethanoate ion CH3COO minus and a hydrogen ion H plus, all in aqueous solution. Since weak acids only partially ionize in solution, then a solution of ethanoic acid would contain a mixture of ethanoic acid molecules, the ethanoate ions, and hydrogen ions. To link the strength of acids to pH value, let us look at the pH scale. So strong acids, pH 0 to 2, will ionize completely in solution, and weak acids, pH 3 to 6, will partially ionize in solution. Now we will examine the same principle for strong and weak alkalis. Recall that an alkali is a base that dissolves in water, otherwise called a soluble base. Like strong acids, a strong alkali ionizes completely, that is, the solute molecules of an alkali will dissociate, releasing the hydroxide ion and the respective cation, which is usually a metal ion. So if you saw our animation to the right of the screen, you notice that we have our cation and our hydroxide ions within the solution. Examples of strong alkalis include sodium hydroxide, chemical formula NaOH. Each molecule of sodium hydroxide in solution will ionize to release one sodium ion, Na+, and one hydroxide ion, OH-. Next is potassium hydroxide, chemical formula KOH, which ionizes to release one potassium ion, K+, and one hydroxide ion, OH-. Like weak acids, weak alkalis partially ionize or dissociate when dissolved in water. That is, only a few alkali molecules dissociate into ions at any given time. We know the reaction is reversible, as the alkali molecules that dissociate into ions, those ions can rejoin to form alkali molecules. So a weak alkali solution will contain alkali molecules as well as the dissociated ions, the cation and the hydroxide ion. An example of a weak alkali is ammonium hydroxide, also known as aqueous ammonia, the chemical formula NH4OH. Aqueous ammonia dissociates to release the ammonium ion NH4+ and the hydroxide ion OH-. To link the strength of alkalis to pH value, let us look at the pH scale. Strong alkalis, pH 11 to 14, will ionize completely in solution. Weak alkalis, pH 8 to 10, will partially ionize in solution. So take note that both weak acids and weak alkalis will only partially ionize in solution, while strong acids and strong alkalis completely ionize in solution. In this section, we will define the term concentration. Concentration has to do with the number of solute particles, whether acid or alkali particles, in a specific volume of solution. In other words, the ratio of water molecules to solute molecules of the acid or the alkali. So the concentration depends on whether there is little or lots of water molecules present in the solution of the acid or the alkali. We will take a look at this shortly. Two terms or words are used to describe the concentration of an acid or an alkali. We use the term concentrated. A concentrated solution has fewer water molecules compared to solute molecules of the acid or the alkali. Or we can say that a concentrated solution has a smaller volume of water in which the solute molecules are dissolved. And the second term is dilute. A dilute solution has more water than solute molecules for the acid or the alkali. Or we can say that the diluted solution contains a large volume of water in which the solute molecules dissolve. So when we use the terms concentrated and dilute, we refer to the concentration of the acid or the alkali. Note that the concentration terms are not specific to acids or alkalis, but are typically used for any solution. For example, we can have a concentrated or dilute salt solution. Sometimes there is the tendency to confuse the terms strength and concentration for acids and alkalis. So in this section, we will distinguish between the two terms. We will use two scenarios to distinguish between the concentration and strength of an acid or alkali, starting with concentrated solutions. Scenario 1, a concentrated weak acid. The solution is concentrated because the ratio of water molecules to solute molecules or ions is low, and in our illustration, we can identify the water molecules by the blue circles. So there are fewer water molecules than the solute molecules or ions in solution. The acid is weak because there are only a few dissociated ions that exist. So what we have present in solution are the acid molecules represented as the orange circle Ha, and a few ions. Those are the hydrogen ions represented by the red circle, and of course the release of the hydrogen ions is what makes this solution acidic. And we also have the corresponding anion, which is represented by the yellow circle. If it were a concentrated weak alkaline solution, there would be alkali molecules, MOH, hydroxide molecules, OH-, and the corresponding cations, M+, all dissolved in a small volume of water. Scenario 2 is a concentrated strong acid. As we learned, the solution is concentrated because there are fewer water molecules compared to solute molecules or ions in the solution. However, the solution is strong because all the acid molecules have dissociated into ions. There are only hydrogen ions present and the associated anions. Notice there are no acid molecules present. In the the case of a concentrated strong alkali, there would be hydroxide ions, OH minus, and the corresponding cations, M plus, dissolved in a small volume of water. We will do the same for dilute solutions. Scenario 1, dilute weak acid. The solution is dilute because the ratio of water molecules to solute molecules or ions is high. As we can see in the illustration, there are many water molecules, the blue circles, compared to the solute particles. The acid solution is weak because only a few acid molecules have dissociated into ions in the solution. The solution contains acid molecules, Ha, the orange circles, hydrogen ions, H+, the red circle, and the corresponding anions, the yellow circles, all dissolved in water. For a dilute weak alkaline solution, there would be alkali molecules, MOH, hydroxide ions, OH minus, and the corresponding cations. They would all be dissolved in a large volume of water. Scenario 2. The solution is dilute because there are more water molecules than solute particles in the solution. The solution is strong because all the acid molecules have dissociated into hydrogen ions and the corresponding anions. Note that there are no acid HA molecules present in the solution. If the solution were a dilute strong alkali, then there would be only hydroxide ions and the corresponding cations dissolved in a large volume of water. So let us summarize the difference between strength and concentration. Strength corresponds to the degree of ionization of the acid or alkali molecules in solution. That is, whether the molecules are partially or completely dissociated. Concentration has to do with the amount of water molecules to solute particles in solution. If there are fewer water molecules to solute molecules, then you have a concentrated solution. If there are more water molecules than solute molecules, you have a dilute solution. So lesson summary. Note that strong acids or alkalis dissociate completely in solution. Examples of strong acids are hydrochloric acid, sulfuric acid, and nitric acid. Examples of strong alkalis, sodium hydroxide and potassium hydroxide. Weak acids and alkalis partially dissociate in solution. Examples of weak acids, methanoic acid, ethanoic acid, and lactic acid. Examples of weak alkalis, ammonium hydroxide, also called aqueous ammonia. Strong and weak acids or alkalis can be concentrated or dilute. A concentrated solution has less water molecules compared to the solute molecules. A dilute solution has more water molecules compared to the solute molecules. It's quiz time. You have 5 seconds to answer each question after it is read aloud. Question 1. Which statement best defines a strong alkali? A. Solutes of the alkali dissociate completely in solution. B. Solutes of the alkali dissociate partially in solution. C. Solutes of the alkali do not dissociate in solution. D. None of the above. The answer is A. Strong alkalis dissociate completely in solution. Question 2. Which acid is an example of a weak acid? A. Nitric acid, B. Sulfuric acid, C. Ethanoic acid, D. Hydrochloric acid. The answer is C. Ethanoic acid is a weak acid. Question 3. Which diagram would represent a concentrated weak acid? So take a look carefully at option A, B, C, and D. Using the key, the blue circle represents the water. You have your dissociated ions, H plus A minus, represented by the red and yellow circles respectively, and of course the undissociated acid molecules, HA. The answer is A. This diagram represents a concentrated weak acid. It is concentrated because the volume of water is less compared to the solute molecules of the acid, and it is a weak acid because only few of the acid molecules have dissociated into ions. Question 4. The diagram to the left represents a solution of sodium hydroxide. Which option best describes the sodium hydroxide solution? A. Weak and concentrated. B. Strong and dilute. C. Weak and dilute. D. Strong and concentrated. The answer is B, strong and dilute. It is strong because all the molecules of the sodium hydroxide have dissociated into ions. We only see ions present. And it's dilute because the volume of water in the solution is greater than the ions present. Question 5. The pH of solution P is 1 and solution R is 9. Which comparison is accurate about solutions P and R? A. Solution P is a weak acid, solution R is a strong alkali. B. Solution P is a weak alkali, solution R is a strong acid. C. Solution P is a strong alkali, solution R is a weak acid. D. Solution P is a strong acid, solution R is a weak alkali. The answer is D. Solution P, having a pH of 1, makes it a strong acid, and solution R, which has a pH of 9, makes it a weak alkali.
We have reached the end of our lesson. If you found this video helpful, remember to like, share, and subscribe. When you subscribe, you will receive notifications as new videos are uploaded. So until next time, I am Teacher with Iri-e-learning.